So we're well aware at the, I guess you could say, limitations of static analysis. Static analysis is when we don't run the malware and we don't exactly know what it does, but at least we can use, programs like strings, for example, to give us some clues as to what it may do. Basic dynamic analysis actually shows you how the malware works under certain conditions. However, with the ability to disassemble the code, like with IDA Pro, of which we'll be doing that next week, we can actually view the code of the malware and try to figure out what it does. Now, it's really important that we take a look at the notion of abstraction. So, the way code is written, the source code kind of defines how close to the, I guess you could say, to the real hardware, because at the end of the day, that's what any program does. It I guess you could say leverages the operating system such that it can potentially tell the operating system via machine code how it can manipulate the various drives and storage and components of a computer to do what the software needs to do to actually facilitate the end goal of the software. And each level of abstraction tells us how close it can get to the actual, I guess you could say, memory, to the actual components of the computer. So starting at the very top, Python is very, very high level. Java gets a little bit closer because Python is completely interpreted. Java turns the source code into what they call bytecode, and then the bytecode gets ultimately interpreted via the Java virtual machine. Now, what makes Java portable is the fact that the Java, there's different flavors of the JVM or Java Virtual Machine. There's JVMs for Unix, there's a JVM for Linux, and there's a JVM for the Win32 architecture. Or so that's Windows, Microsoft Windows, either 32 or Microsoft Windows 64. Okay, so there is a JVM for basically every OS category that there is out there. So the bytecode. So when you compile Java code, it compiles not into machine code, but into bytecode, of which the JVM can run on different systems. That's how Java defines portability. Now, C, of which we've been doing labs in C, it operates such that when you compile C code, okay, it compiles into the machine language that is befitting for that system. Okay, so there's a compiler for Win32, there's a compiler for Linux, and there's a compiler for everything in between. Now, assembly is machine code that is just more readable machine code because assembly has what we call low level instructions. Now, the code level, here is how the compiler relates to the CPU. So the malware author, in this case, writes this in C, and then it gets compiled into actual machine code. So that's why we're using, C in our examples, because if we use Java, the problem with Java, and I'll write it in pen, as I said, okay, so let's, as a comparison, C, when it gets compiled, it literally gets compiled into zeros and ones that the machine can understand. And when the reason why we have Assembly language just is a more readable reference of zeros and ones. So this is C. With Java, and I'll just say J because my writing is horrible. All right, I'll write Java just so we can laugh at my horrible handwriting here. Java does not get compiled into those zeros and ones. It gets compiled into bytecode. I'll just say BC, and from the BC, it gets interpreted by the JVM or Java Virtual Machine, and then the Java Virtual Machine basically works with the individual OSs and tells them in terms of the zeros and ones that the hardware actually understands. Okay, so that is uh, that is why we generally look at C, because we can actually see the zeros and ones now, and then we can use like IDA Pro to disassemble it into the assembly code, which has a bunch of mnemonics like push, move, and subtract, and we can actually see how it reacts with the various storage components within the CPU. Okay, let's take a look at the hardware level. So hardware, and of course, this is going to be like layer one in the OSI model, right? And we talked about the various pieces of logic. So XOR or exclusive OR is if you have the various combinations of zeros and ones that you could have when you compare two digits. We have 1 1, 1 0 0 1, and then 0 0. Exclusive OR says the only time it's true is when there's only one that is true. So this is true or translates to 1. This would translate into 1, and the other ones this would be false. That's false, so that translates into 0. That translates into 0. So that is exclusive OR. Now, when it comes to ANDing right here, ANDing says, hey, the result of this will be true, but in order for it to be true, both sides have to be true. All the rest are going to be false. So that's false. That's false. And this is false. Now, we have, that is ANDing. Or, of course, is only one side has to be true. And the only time it's false is when both sides are 0. In every other case, it is true. Now, it's critical to understand when you're looking at circuitry and the ones and zeros and how the processor, the CPU look, and the reason why we're even talking about ones and zeros, and the reason why we're talking about XORing and ORing is because of the very fact that these are the operations that your computer actually uses, because that's all it knows is ones and zeros. Okay, and it uses this elemental logic to make basic decisions for your computer. Everything else is just noise. It all comes down to the ones and zeros. And the other aspect is it actually, ones and zeros they are not immutable. So the operations of this will actually result in whatever this is. So if you're XORing 1 and 0, it will equal 1. If you're ANDing them, it will equal 0. If you're ORing them, it will equal 1. So these are real operations. It's not like a string in Python or a string in computer languages in which it is immutable. These are real operations that are going on in the background. Okay. Microcode is an example of what we call firmware. okay? And we have the idea of machine codes. So operator codes tell the processors, it tells the processors to do something, okay? And it's written, of course, when the program is basically developed. So you're using syntax like, for example, for loops. And a for loop can transform or mutate a value. So when you mutate or do anything, it's going to translate that into instructions to the CPU. So these instructions we can see in assembly language are what we call mnemonics, or little human readable versions of the instructions. Examples are push pop. Uh, NOP is basically no, do nothing. Okay, NOP, and no, like no process. We have move, and then we have jump. So the disassembler generates this language based on the original source code. Okay, and unfortunately, when it comes to assembly language, it is the most abstract language we can glean from the machine code, because they're literally getting the assembly instructions from the machine code. Okay, as I said, there's interpreted languages. Okay, and the code is not compiled into machine code. It is translated into bytecode. Okay, and so the reason why we use C and not Java, C Sharp, Perl.NET, or Python is because of the concept of reverse engineering, the idea of disassembly. Okay, the fact is that malware on a disk, like, and it's not just malware uh, that's in binary form. Literally every program is in a binary form. Okay, so what disassembly does, it translates the binary code into assembly language like IDA Pro. And as I said, different versions are there for each processor. Of course, x86 is the most common. Okay, maybe not the 32-bit Intel, but it is the most common. So the x86 architecture uses what they call the von Neumann architecture. Okay, we start off with the CPU that executes the code. The RAM stores the data. Now, when I say data, okay, it has to do with the actual instructions of the CPU, not like data like, the data that Amazon keeps track for us. I'm talking about the data that gives the CPU like very elemental instructions. Okay, and then we have the input output system that actually interfaces with your components of your computer. Your things like your hard disk, your keyboard, your monitor. Now, now notice I'm careful. I did not mention the graphics cards, because although you could say that the CPU points to your graphics card, maybe in some ways, the graphics card CPU essentially is its own complete thing. That's why when people are building their fantastic rigs, I keep telling them, you don't have to worry about your actual processor. If you want a screaming system, you want to max out your GPU, your graphics card. You don't worry so much about your CPU. Okay. Moving on. Moving on, other things include the control unit right here. Now, your control unit uh, fetches instructions from RAM using a register named the instruction pointer. Okay. Now the registers essentially right here are essentially data storage within the CPU. So they store basic data. And the reason why registers are store data is because it is faster than RAM. Okay, let's take a look at the RAM in of itself. On the bottom is what we call data. Data is placed in RAM when a program loads. Okay, so the data, and these values are static and they cannot change while the program is running. They're also global, available to any part of the program. Now, the code is instructions by or instructions for the CPU. It controls what the program does. Okay, the heap is what we call dynamic memory or object oriented memory, and that can change frequently during the program operation. The stack includes local variables and parameters for the functions. It helps the program flow. So if you create we'll just call it a function right here. We'll call it f, and the function is going to take, parameters right here, a and b. Now those parameters are going to be defined via the instance variables, okay, of any object, and those IVs and local variables, okay, they are going to be stored in the stack, and stack memory is going to be more efficient than object-oriented memory or heap, because heap exists in a unregulated, if you will, format, because it's object oriented. You never know how big that sucker is going to be, because every object is kind of different. Objects are like snowflakes. Okay. Anyways, let's take a look at instructions. An instruction is what we call a mnemonic followed by operand. Take a look at this. Here is move. So in other words, it's going to move 42, the value of 42, into the ECX storage. Okay, and we have move ECX is OXB9 in hexadecimal. So if you break this down into zeros and ones, you could represent it as B9. And just so you know, I purposely, in avoiding mentioning OX, I just said B9 because OX is just telling us that B9 is in hexadecimal. Okay, now the value of 42 is OX42 right here. All right, now because of this, the binary of this instruction is represented by the hexadecimal number of B9, 42, and then all these zeros. Okay, now let's take a look at how this is represented. It's represented via an idea of what we call endianness. There's big endian, in which the most significant value, or the most significant byte is first. So because OX42 is a 64-bit value, okay, it would end in 42. Little endian is least significant byte first, so that's why 42 is represented in the beginning here. Now, interestingly enough, network data uses big endian, and I wish I had that other PowerPoint handy. You recall, like, for example, that Class A will always have, what did I say? Class A will always have like a 1-0 leading it, or my apologies. It's been a day or so before that last one. What I'm saying is that we recognize that, for example, the IP address of 10.0.0, let's say .1, we know it's a Class A. Why do we know it's a Class A? It's because of the first octet. So the first octet determines the default subnet mask of the IP address, and that is because network data, like IP addresses, are big endian, which means the most significant value is first. Okay, that is the big deal regarding that. Let's take a look at, as I said, IP addresses. Now, here is 127.0.0.1 in hex, or 7F001. So how the heck does 127.0.0.1 become 7F001? But if you take a look at this, it's kind of obvious, I guess. The 001 is going to be translated, and you can match it up to this 0, 0, and then 1. So that's 001, and that is 001. I mean, that's kind of obvious. What about this 7F? Okay, so why is 7F presented here first? Well, it says it is what they call big endian, which is the most significant byte first. So that's 7F, but where do we get 7F? So if we go to the next slide here, we have 127 is actually in binary 0111111, which makes sense because 128 is 1 bit below 128, or 127 is 1 bit below 128, and 128 would be 1, and then all these would be 0. So it stands corrected that 0111111. The next, if you add 1 to this, it's going to be 1, which is 1. If you add 1 to this, which is 127, it's the result of adding 1 would be 1, and all the rest are zeros. That's just the way binary is. For example, if you have 1 1 0, and you, or excuse me, if you have 0 1 1, and the next, literally the next number is 100, and then the next one after that is 101. It's just binary counting, right? So if we took a look at this, oops, forget that. I apologize. I should have kept it. Okay. Anyways, if we take a look at this, it is 0 1 1 1 1 1 1. The next number is going to be 1 0 0 0 0 0, so which is 128. So 127 is 0 1 1 1 1 1 1 1. Now, in the step-by-step method from converting binary to hexadecimal, we first aggregate these into two sections. We aggregate them into nuggets. And the first one, 1111, is then F in hexadecimal. And this is 111, so we add 1 plus 2 plus 4, and that is 7. So this is 7F. So it makes sense that because IP addresses are big endian, okay, it stands to reason that the most significant bit is first. So we have 7F, and all the rest are zeros ending with a 1. And then, of course, the OX is silent. It's stored in RAM, however, because we talked about programming. The x86 programming is little endian. So it's stored in RAM is the exact opposite, 010000 Let's take a look at operands. Fixed values like negative x42. Okay. Those are operands. What I'm saying is that there's actions. Okay. An action is an operator. So for example, x. Well, I should have done that. But let's say we did x multiplied, and now you know why I shouldn't have done that, but anyways, by y, that is going to be xy. And when we take a look at this, this is the operator, and this is operand 1 and operand 2. Okay, so we have registers and we have memory addresses. Now, memory addresses, I wanted to tell you, are in open and closed straight brackets. Okay, there's different registers. We have the general registers like EAX, okay, EBX, ECX, and so on and so forth. General registers are used by the CPU during execution. Segment registers are used to track sections of memory if there is an overflow. Status flags are to give it the instructions after a decision is made, and the instruction pointer is the address of the next instruction to execute, known as a pointer, kind of like C and C++ pointers. It gives us the memory address. Okay, general registers, 32 bits in size, but they can also be, as you can see, 8 bits. So when it's 8 bits, we can see we have 8 bits, and it can be translated into hexadecimal right here. So you can see the more registers, or the larger the size of the register, the more robust I guess you could say the instructions can be. Okay, now general registers typically store memory locations or data, and they are interchangeable, which means they are changeable. Okay, some instructions reference specific registers like multiplication and division use EAX and EDX. Okay, flags are 32 bits, and each bit is a flag. Okay, set 1 or cleared 0. So, for example, the 0 flag is set when the result of the operation is 0. The CF flag is ticked if the operation is too large or small for the destination. Okay, and there's other different types of flags. Okay, and when we talk about the extended instruction pointer, it contains the memory address of the next instruction to be executed. Let's take a look at simple instructions here. We have move. So the move begins with a destination, and it says, okay, it'll start here at the source, but by the time it's done, it will be defined as part of the destination. Okay. So for example, when EBX right here is in brackets, straight brackets, it means not the value of EBX. It means the memory location of EBX pointed to by EBX. Okay, so for example, move EAX, EBX, it means move the contents of EBX into EAX. Here, move EAX, it says copy value 42 into the EAX register or storage. Here, move EAX, that means whatever the location of 403, 37 64, whatever's in that location, copies that into EAX. Now, LEA, or load effective address, that is going to load the source right here, or here, EBX not plus 8, not the location where it is, like the actual EBAX, and it's going to place it into EAX. Now, that is different than the idea of comparing. Comparing moves the location, whatever is pointed to by in the location of EBX plus 8 gets moved into EAX. So take a look at this one. This is kind of like a basic summary of how your CPU treats these various commands. So we start off with EAX initially is basically zeros. It's null. Now, EAX, as I said, is a register, which is a storage place in memory. Now, registers are used heavily in CPUs because it is faster than retrieving from RAM. Okay? Now, EBX contains 00B340, okay, which refers to 0000. Okay, now here it says EBX is set to this. At address OXB348 is the value 20 right here. Now the instruction move EAX EB plus 8 places the value 020 because it is EBX, which is ends in 40, but it's adding 8. So the fact that it's in open and closed brackets means that it's not storing EBX plus 8 literally. It's not storing 48 into EAX. It is in fact storing 020 into 08 because 020 was obtained from memory. That's what the brackets mean. Now the instruction LEA 8 EAX, this literally places the value B348 right here into EAX. Let's take a look at arithmetic subtracts, and adds, increments, decrements. Okay. Now, no OP basically means no operation. It does nothing, and we're going to talk more about that next week. Let's take a look at the stack. Now, the stack is what it says it does. It stores simple variables, those primitive variables, those things that are like actual arguments, and it stores it in a stack fashion. Like the way we can visualize it is imagine somebody was stacking. If you worked at a restaurant and you had a big old stack of plates right here. So the last plate that was placed is going to be the first one that is going to be removed. That's why stack logic is LIFO, last in, last out. Okay, so the top of the stack is what we call the extended stack pointer, and the bottom, because it's supporting all the rest, is referred to as the base pointer. Push puts data on the stack. Pop takes data off the stack. So we're going to push more plates on top of this heap. And when we remove a plate, it's like we popped plates from the stack. We have other use functions are call, leave, enter, return. Okay. As I said, the small programs that do one thing in return, like printf, we have the instructions at the start of a function that prepare the stack, and instructions at the end of a function that restore the stack. Okay, the stack grows up towards 0. Okay, so we can see that, the frames are taken from the top. So things with this in the stack frame include local variables, return addresses, basic arguments, and things like that. Now, when it comes to conditionals, we have testing, which compares two values, but it does not alter them. Okay, we have test EAX EAX and sets the 0 flag if EAX is 0. We have branching here. It jumps to the location. It jumps to this location if the 0 flag right here is set, and it jumps to location if the 0 flag right here is cleared, no 0 or NZ. Notice we have the C main method. Every C program, like Java, has a main function. And the main function is defined as the number of arguments on the command line. And we have the pointer to an array of names containing the argument. That is the international symbol of pointer, but it's actually the pointer of a pointer. So if we had, let me visualize basic memory here. So we have a pointer here, and this is actually pointing to the pointer, and the pointer actually ultimately points to an actual place in memory. An example is we have 3 arguments here. So there are three arguments, and argv0 is CP, argv1 refers to foo, and arg2 refers to bar. Okay, so the whole point of this exercise, this PowerPoint, is to get you a little bit familiar with the intricacies of assembly. We just touched the surface. If you want to study assembly, if you want to study the little nuances, there are books that are available that show you how you can use assembly to actually hack real programs. And you can be very, very dangerous, and you can potentially make yourself a millionaire, but that is up to you. And I would never want to teach you anything that could make you too dangerous, because that means liability against me, the school, and all of that. So, thank you very much for taking the time to listen.